right, well, good morning and happy Friday. Week 9, just one more week of lecture and finals week, and then a small break. Okay, we've been looking at these kind of resampling methods for answering statistical questions and really to give us an estimate of the sampling distribution. We saw randomization tests on Monday. On Wednesday, we first saw the bootstrap, and we did some hypothesis testing with bootstrap. And today we will do more bootstrap, but this time with library boot. So we when I introduced bootstrap on Wednesday, I said the main idea is you're going to assume your sample of data is representative of the population, and therefore we can kind of make a whole bunch of duplicates of it and call that our estimate of the population, and we can do that by just resampling our data with replacement. And I wrote some code, and it works perfectly fine for doing some bootstrap. Although probably in practice, if you wanted to do bootstrap, you will probably use library boot. Okay, so library boot is a popular library for doing bootstrap. It comes with some additional functions that we can use for calculating confidence intervals and things of that sort. Okay, so here are other kind of use cases that we have beyond hypothesis tests that we can use bootstrap for, and you're not limited to these, but these are often popular cases of using bootstrap. So we can make confidence intervals for parameters such as the mean, and we already know how to make confidence intervals for the mean from our intro stats class. Central limit theorem applies, so you go use the t-distribution, or you go 1.96 standard errors above or below the mean, things like that. But then other statistics like your median or your variance or quantiles and things like that, those might be a little bit tougher, okay, as far as making a confidence interval, just because things like the central limit theorem don't really apply to the median and stuff like that. Okay, there are if you wanted to work with what we call robust statistics like the median, we have other ones like the trimmed mean. The trimmed mean basically takes your data set and throws away the largest and smallest values or your outliers or things like that, and calculates the mean on a subset of your data rather than the whole set, so that it's not going to be as skewed and things like that. These types of estimators often require resampling for inference, just because trying to do figure out your standard error and analytically for these things gets a lot more complicated. What's the standard error after you've thrown away some of your values and stuff? That's a little bit tougher. Okay, you can also do bootstrap for things like regression models. So you can try to estimate how much do your regression coefficients vary from one sample to another random sample. Maybe you don't want to assume everything. Some of these assumptions where your errors are normally distributed, this is often very difficult to achieve in real life. So some of you guys are doing 101A projects and things like that, and when you do your analysis to see are your assumptions met, a lot of times you're like, I don't know, is this normal enough? And so I think when you call summary on a linear regression model, it automatically kind of puts in a standard error, and it calculates your significance and all of these things, and they're very kind of handy and useful, and it's great. But again, all of those work off of the assumption that your errors are normally distributed, and sometimes you just the data just doesn't cooperate with that assumption, okay? And so, can you still use a linear model and do some inference on that? Yeah, but we probably want to use Bootstrap for something like that, okay? In cases where these assumptions aren't met. There's a lot more like complicated forms of Bootstrap. I'm not even going to bother touching on these things, but you have like the block Bootstrap and the cluster Bootstrap and things like that. I'm just going to say you can look it up on your own time if you're more interested in some of these other forms of Bootstrap, where it's basically, how do we, in everything, we're just trying to estimate, sampling distributions, recognizing we don't have full access to the population. Okay, so anyway, to use library boot, you call library boot. If you don't have it installed, you call install.package as boot, and again, it supports non-parametric as well as parametric approaches and other of these specialized things. I'm going to just kind of show you examples of non-parametric Bootstrap. But again, there's lots of resources. It is a popular package. So that's the great thing about the internet, is that if something is popular enough, there's going to be a lot of resources to help you learn how to use it. Okay. All right. Basically the core function that you're going to be using in that boot package is the function boot, and this is going to perform Bootstrap for you. And what it's going to do is it's going to do Bootstrap replicates for some user-defined statistic, okay? Now, the user-defined statistic can be as simple as the mean or the median or whatever it might be, but you will have to write your own function that goes into the boot when you use boot. And I will talk about this. Basically, this is the statistic for which we are going to create our sampling distribution. So again, the sampling distribution is the idea that if I take a random sample and I calculate a statistic, and you take a random sample and you calculate the same statistic based on your random sample of data, we're going to get slightly different values. And what kind of distribution of values can we get? That's going to be our sampling distribution. And so whatever that statistic is, whether it's the mean, the median, or the third largest value, you need a function, okay, a user-defined function that's going to calculate that statistic, okay? And then, boot, this thing supports all kinds of stuff, non-parametric methods, which is what we're going to look at. And there's other forms of Bootstrap that I am not super familiar with, okay? I'm going to mostly cover just ordinary Bootstrap. But you have, I guess these other kind of things. Antithetic, I don't know what that is. The balanced Bootstrap, stratified Bootstrap, different kinds of things that control how we resample our values. We have parametric functions and stuff like that. Okay. And so these are all of the different kind of arguments, and you can also do like parallel processing and things. But the three primary arguments that we need to worry about will be the data, the statistic, and R, okay? The data is going to be your data set that you want to resample, okay? So this is the data set that we're hoping is representative of the population, and we're going to resample it with replacement. That data can be a vector, a matrix, or a data frame. If it is a matrix or a data frame, each row is treated as one observation. So it's assuming the data is in tidy form, where each row is an observation. If your data comes in and that's not the case, then you might have to use tidyr to reshape. You either have to pivot it longer or something like that in order to get, or pivot wider, in order to get your data into this tidy form where each row is an observation. And then the statistic is going to be a function that you write that's going to compute the statistic of interest. And that function that you write will always take in two arguments. One is going to be the data, and the other is going to be your index, okay, the indices. So the original data, and then the vector of indices, frequencies or weights or whatever, to define your Bootstrap sample. Okay, and then R is going to be some number, like a big number, like 1,000, maybe 10,000. And this is going to be how many replicates you want it to perform. Okay. the way Boot works is it resamples indices rather than the raw values in the data themselves. Okay, so it's going to look at how big your data set is, so how many rows are in your data set, or if it's a vector, just the length. But if you have like a bunch of rows, it's going to sample a random set of those row index values. Okay, then it takes those index values and it subsets the original data, and then it calculates the statistic to that subset of data. Okay, and by resampling indices rather than the actual values themselves, it's just going to be a little bit more memory efficient. Okay, and it also allows for us to do slightly more flexible resampling methods and things like that. So just to kind of show you that these things are equivalent, okay, here I am going to set my population to be the 26 letters of the alphabet. Okay, so my population is going to be the letters, and I could sample those values, the letters, directly. Okay, so if I do set seed 5 and I say sample with replacement, I want 10 values. I select the letters B, K, Y, O, K, Y, I, U, G, W. And just kind of by coincidence, I end up selecting K twice and Y twice. Okay. What resampling the indices will do is it says, okay, well, how many values do we have in the population? We have 26 values. So I'm going to sample index values 1 through 26. I'm going to sample 10 of those with replacement. What are the index values I get? I get 2, 11, 25, 15, 11, 25, 9, 21, 7, and 23. And again, we can see I selected 11 twice and 25 twice. And so once I have these index values, I subset the population based on those resampled index values that I have. And yeah, 11 corresponds to K, 25 corresponds to Y, and I get the exact same set of values, okay? BKY, OKY, I have BKY, OKY, right? So it's just the same things, but here I'm sampling index values, kind of positions first, and then I use that to subset the population. And this is basically how Bootstrap does it. Rather than sampling the original kind of population directly, it first does the index values, then it subsets the population based on those index values. Okay, so we'll work through an example. We'll look at the IRIS dataset. I think we're familiar with the IRIS dataset. This is like a classic old data. It's like over 100 years old now, okay? And Ronald Fisher, for whom we've named the F distribution, and we owe a lot of kind of statistics knowledge to, wrote a kind of a famous paper using the iris flower data set, and it's just kind of like this very popular data set, especially for like classification problems, okay? Because we have 3 species, Setosa, versicolor, virginica. We have 50 observations from each of these 3 species, and we have these, nice numeric variables, okay? And so our numeric variables are sepal length, sepal width, petal length, and petal width. And I didn't know what a sepal was until I looked at this. But here is a diagram of an iris, okay, from the USDA Flower Service, or Forest Service, sorry. Prior to learning about the data set and this, I would have just called all of these things petals, but apparently in an iris, the bigger things are not petals, they are sepals or falls. And then the smaller ones that stand up a little bit more upright, these are known as the standard or the petals, okay? So when you look at an iris or something, this thing is the fall or the sepal, and then the things that stand up, those are the standards or the petals. And so there's a difference between them. So you can look at the iris flower parts, and we have the sepals and the petals, okay? So that's what we have. And someone measured 50 Setosa iris flowers, their sepals length and width, and the petals length and width, and then the same for versicolor and virginica. And so anyway, this is kind of what the data look like. Here's I did dplyr and I summarized these things on the sepal length and width and petal length and width and things like that. And here's a plot of all of these things. And yeah, we can look at, they're colored by their species. So red is Setosa, green is versicolor, blue is virginica. And really, like if you wanted to classify these things, you could probably do a pretty decent job just by looking at petal width. You can say, all right, if the petal width is under, 0.9, that's going to be Setosa. And if it's between 0.9 and 1.7, 1.6, something around there, that's going to be versicolor, and anything greater than 1.7 is going to be virginica. You'll probably get 90-something% accuracy just based on that one variable. And if you take in, petal length and petal width, you can do kind of like even a better job. Okay, but if you're doing something like sepal length, sepal length over here for Setosa, the average is around 5, but there's some spread. It goes as high as 6 and as low as 4.4 or whatever. Okay, and then green is versicolor, and looks like the average is around 5.9, but it goes as low as 4.8 and as high as 7. It looks like in green, right? Virginica, there's also a lot of overlap with versicolor and things like that. So, depending on the variable, it might be a little bit tough. What we're going to do is we're going to do just a simple t-test, okay? Or a simple hypothesis test comparing the mean, and we'll do the mean sepal length of Setosa and the mean sepal length of versicolor, okay? So I have Setosa right here in red, sepal length, and sepal length for versicolor in green, and we just want to compare the means of these two groups, okay? The way it's arranged in the data frame is arranged so that the first 50 values are Setosa, and then observations 51 through 100 are versicolor, and then observations 101 through 150 are virginica. But here we're just going to compare Setosa versus versicolor. So I'm just going to look at the first 100 values, and we'll say, okay, the first 50 are Setosa, and I want to compare the sepal length of my first 50 Setosa values, which are Setosa, and then I'm going to look at the next 50, which are versicolor. So I'm going to do sepal length 51 through 100. I do a t-test, and we get a few things, right? The mean of Setosa is 5.006. The mean of versicolor is 5.936. So we have a difference of, 0.93 between the means. And we ask, is that difference significant compared to, its standard error? And the answer is a resounding yes, because my test statistic t is like negative 10.5, where over 10 and a half standard errors from the mean. Usually anything over 2.5, that's going to be pretty significant. And here I'm 10 and a half standard errors from the mean. And so my p-value is practically 0, 2.2 times 10 to the negative 16. So we have a p-value that's practically 0. So that's my t-test, but what we can do is we can do a bootstrap hypothesis test, okay? And so we'll do bootstrap. Let me go ahead and give you your first ViewQuiz answer, which is the letter E. E as in elephant. E is going to be your first ViewQuiz answer. All right, so here I'm going to run the same code in two different ways, or run the same, operation in two different ways. One is I'm going to resample the values directly, and then the second is I'm going to resample indices and then subset my data and then calculate my statistics. So here, if I wanted to resample the values directly, I would say, okay, well, if the null hypothesis were true, right? So then my null hypothesis, I'm testing to see if there's a difference between the mean sepal length of Setosa and the mean sepal length of versicolor. The null hypothesis would be that there's no difference. And if there is no difference, if that null hypothesis were true, my population, I would pool all 100 values together. I would just say, basically my Setosa values are coming from the same kind of population as the versicolor values. If the null hypothesis were true, I would pool all 100 values together. And so that's what I do. I say sepal length, take all 100 values, 1 through 100, and that's going to be my population for Bootstrap. and then I will sample 50 values with replacement from that population for group A, and I'm going to sample 50 values with replacement from that same population for group B. Okay. I calculate the mean of group A, the mean of group B, I take the difference between them and I store that as differences. Again, when you do bootstrap, you want to ask yourself, what does the population look like if the null hypothesis were true? And in this case, if the null hypothesis were true, we can pool both the setosa and the versicolor values together. Okay. A common mistake students make is they resample the setosa values separately from the versicolor values. They resample them separately, and in some cases you might want to do that if you're doing some kind of stratified thing or if you had a different null hypothesis, but that's not what we would do for this particular hypothesis test. For this hypothesis test, the null hypothesis says they're basically coming from the same population, so you pool them all together and you resample that because you want to know what kind of values do you get if the null hypothesis were true. Okay, and so if that null hypothesis were true, no surprise, our median difference is 0. Our mean difference is very close to 0, which is exactly what we would expect if the null hypothesis were true. Okay, so yeah, I guess that's kind of a little bit of a sanity check, as you say, okay, well, if the null hypothesis is true, what should my sampling distribution look like? And then so when you look at all of the different differences, your sampling distribution of differences, it should reflect what you should get if the null hypothesis were true. So in our case, if the null hypothesis were true, I'm expecting my mean to be close to 0, and that's exactly what I get. Okay, and in our hypothesis test, we observed a difference of 0.93. Okay, negative 0.93. If I mean of x 5.006, mean of y 5.936, so I'm getting a difference of negative 0.93. And in my 10,000 observations, not once did I get negative 0.93. The most negative difference I got was negative 0.47. The most positive difference I got was 0.552. So nowhere did I get anywhere close to 0.93. So that would be evidence that my difference seems significant. Okay, but here I resampled my data directly. I want to show you what our code would look like if I resampled indices. Okay, so here I'm pooling again my setosa and versicolor values together. So my data set has 100 values in total, and so I'm going to have the index values will be 1 through 100. And what I'm going to do is I'm going to sample those 100 values, and so I'm going to get my resampled indices. Okay, my resampled indices, I'm going to select 100 values with replacement from 1 through 100. So now I'm going to subset my data, the iris data set, using those resampled indices. Okay, so I take iris and I subset it based on the resampled indices. That's going to be my resampled data. And now that I have my resampled data, I'm going to take observations 1 through 50, call that group A. I'm going to take observations 51 through 100, call that group B, calculate the mean of group A and the mean of group B, and I'm going to store that in as my differences. Okay, so just a small change here. When I call sample, I resample just the index values 1 through 100 with replacement. And when I do that, I get the same outputs. Okay, I get, my most negative difference was negative 0.47. My most positive difference was 0.552. My mean difference is right around 0.00268. And in fact, if I ask, are all of my values differences and differences B? So these are the differences I got when I resampled my values directly. Are they the same as when I resampled the indices? I end up getting the exact same results. Okay, same results here. And so this is basically what boot, the function in the boot library does, is it resamples the indices. And so what we need to do is we need to write a function ourselves that will calculate the statistic of interest. Okay, and it's going to calculate the statistic of interest based on a subset of the data. And so this function that we write has to take in two arguments. One is going to be the data, and the other is going to be the indices. In your function, you do not need to perform the resampling of indexes. Okay, that is going to be handled by the boot function. So when you call boot, it will handle the resampling of the indexes itself. It passes the resampled index to this function. So it's going. This function is going to receive the resampled indices, and based on the resampled indices, this function needs to calculate our statistic. So our statistic here is going to be done by taking the data, subsetting it to those resampled indices. So I'm going to do data subset index comma, because my data is going to be my iris data set. So I'm basically subsetting iris based on the indices. And that's going to form my resampled data. And now from my resampled data, I'm going to take sepal length. We'll take the first 50 values, call that group A. Then I'll take observations 51 through 100, call that group B. Calculate the mean of group A, the mean of group B. That's going to be my difference, and that's what I'm going to return here. Okay, so very, very similar to this, where I basically have my resampled data here by taking iris and subsetting to the resampled indices. And here we're doing the same kind of thing. I have my resampled data, and I'm just going to take these arguments, data and index, subset my data based on the resampled indices. Calculate this and this. I get group A and group B, first 50 and the next 50. Calculate the mean of each of them, take the difference, and store that. Or return that, I should say. So that's going to be the statistic function. Then running boot works like this. I call boot, and the data that I'm going to use are the setosa and versicolor observations. I'm just going to take the first 100 rows in iris. Then I'm going to calculate the statistic using the difference function. So this difference function that I just wrote, that's going to be the statistic function. Okay, and then I say do 10,000 of these replicates. Okay, and that's that. And so when we run it, I'm going to store it as boot results. Boot results comes back as a big list. A couple things. T0 is what you would get if you didn't do any bootstrap resampling at all. If you just passed for the index 1 through 100. Okay, you didn't do any resampling. And so this is basically going to be your observed statistic, right? Negative 0.93 is just my observed statistic. If I calculate the mean of setosa, I get 5.006, and the mean of versicolor, which is the next 50 values, I get 5.936. I get a difference of negative 0.93 between these two means, and that's what we get here for my T0. T is the a vector or matrix of all of kind of the different observations that I get, different statistic values I get for my resampled data sets. So here I said, give me 10,000 replicates. So T is going to have 10,000 values. And when I resampled my data and I calculated the difference between group A and group B, I got negative 0.92. And then when I did it again, I got negative 0.348. And when I did it again, I got negative 0.146. And this is just going to be the vector of all of the different values I get of my statistic for the different bootstrap replicates or bootstrap resamples. R is going to have the number of replicates, okay? And then it has a bunch of other information. It has a copy of basically the data that you passed it, your data frame, and then other things related to information about it. You also have options for strata and weights. Here, I don't have any strata. Everything's just kind of in the same group. But if you wanted to kind of resample within strata and for some, if the situation calls for it, you can do that. Here, everything is weighted the same. All 100 observations have the same weight of 0.01. But you could provide a vector of weights so that certain values get resampled more frequently than other values and stuff like that. Okay. The individual bootstrap results are stored in this vector $t. I can ask about the summary values there. And it says, your minimum is negative 0.434 and your maximum difference that we observed was 0.506, which is slightly different from our values. And even though I set the seed over here, the way it performs the resampling of indexes isn't exactly the same as our manual code, but that's fine. This is the results of the bootstrap. Okay, and so if we are doing our hypothesis test, my empirical p-value is going to say, well, how often did my resampled results produce a difference as extreme as the one I observed? Okay, the difference I observed is negative 0.93, 5.006 versus 5.936. My observed difference is negative 0.93. When I did bootstrap, okay, that difference is also stored in T0. I got negative 0.93, and I asked, how often did my random bootstrap replicates produce a value greater than 0.93, absolute value? I say, how often were my absolute values greater than 0.93? And that happened 0 times. Okay, out of 10,000 replicates, again, the greatest difference I observed was 0.506, and the most negative value I observed was negative 0.434. So nothing greater than 0.93. So my empirical p-value is 0. Okay, empirical p-value basically happened 0 times out of 10,000, and that aligns with the t-test that we performed back here. The t-test says your p-value is on the order of 2.2 times 10 to the negative 16. So, practically 0. Like, you'd have to do, like a trillion of these things, and maybe it'll happen once, okay? And here we can see, yeah, you know what? Here are my 10,000 results. As we would expect, if the null hypothesis were true, we would expect to see a difference of 0, and my 10,000 replicates indeed are centered around 0. My test statistic that I observed is this dotted line out here at negative 0.93. That my sampling distribution isn't even close to that. So again, my p-value, empirical p-value is 0. My theoretic p-value, according to the t-test, is like 10 to the negative 16, very close to 0. This looks very, my sampling distribution looks normally distributed. And in this case, it makes sense to have a normally distributed sampling distribution. In some cases, it's not going to be normally distributed, and that's okay, all right? We're able to still kind of estimate our sampling distribution just by resampling our data, and so your sampling distribution might not be normally distributed, and that's okay. When you're doing bootstrap, you don't have to worry about that, okay? If you're doing classical statistic methods, okay, where you're assuming normality, doing a t-test, things like that, then yes, you want to make sure your sampling distribution is normal. But in our case, with bootstrap, we're not too worried. You can look at the, produce a density curve of your results here. Again, normally distributed, centered around 0. When you do boot, you can also create confidence intervals. And that's just done by doing boot.ci on your boot results. Now, here, I get an error when I try to create our confidence intervals. And that is because when we calculate confidence intervals, we need to get a standard error estimate. And basically, here, I don't have a standard error because my empirical p-value was 0. Not once did I get a resampled value that was as extreme as my observed difference. So I get my empirical p-value is 0, and that results in errors here, okay? I'm not able to calculate any kind of bootstrap variance or anything like that in this particular situation because I have an empirical p-value of 0. I've got a couple more examples where we are able to do the bootstrap confidence interval, okay? And so we do boot.ci. When you call boot.ci, it actually, I think it'll produce 4 of them. Here I have 3 of them described. The 4th one I'm leaving off is, I think, the normal distribution-based confidence interval, and that basically just goes 1.96 standard errors above and below your mean. But we won't worry about that. But the other 3 confidence intervals, we have the percentile-based confidence interval, the basic confidence interval, and then the bias-corrected and accelerated confidence interval. Okay, the percentile confidence interval I think is the kind of simplest and most straightforward. If you do 10,000 replicates, you're just looking for the middle 95%. Okay, so with 10,000 replicates, we're going to throw away the bottom 2.5% and the top 2.5%. So with 10,000 replicates, my bottom 2.5%, I'm going to throw away like 250 of them, and the top 2.5, I throw away 250. I'm basically go from the 251st value to the 9,749th value or something, or the I go with my quantiles, and that's going to form my percentile confidence interval. I just kind of go for the middle 95% in of the different bootstrap replicates that I get. Okay, that's the percentile interval. The basic interval here does something similar, but it pivots your data around your T0. So here we're going to assume that when you do your bootstrap replicates, the 97.5 percentile is going to be a large value. Okay, so if our 97.5 percentile is a large value, we say how much greater than T0 is that difference. So I say, what's the difference between 0.975 and T0? Like, what's the difference between the observed value and my 97.5 percentile? And I take that difference, okay, T 0.975 minus T0, and then I say, okay, well, whatever that difference is, I'm going to flip it around below T0. That's going to form my lower bound. Okay, so my lower bound is going to be equal to the difference between the 97.5 percentile and T0. Okay, and so when you do that, you get 2 T0 minus 0.975. And then by the same logic for the upper bound, I say, okay, how far below is my 2.5 percentile from T0? Whatever that distance is, I'm going to form as my upper bound. I flip it around or pivot around my observed value of T0, and that's going to form my upper bound. And so my 95% confidence interval will be, basically this, my lower and my upper bound. Okay? So that's the basic interval. And then the last one is the bias corrected and accelerated interval. And to be honest, this is the one I understand the least because I didn't bother going through all of the math behind the calculations here. It is actually like to do this yourself, it is quite computationally involved, okay? But it corrects for bias being kind of like if your observed statistic T0 is not at the center of the bootstrap distribution, we say there's a little bit of bias. If the shape of the bootstrap distribution is skewed, there's like what we call an acceleration factor. And so the bias corrected and accelerated interval kind of brings in a bias correction factor and an acceleration factor, which affects, how where the center is going to be and how the tails get kind of moved in. And so anyway, it's computationally involved, but the computer handles it for us. Okay, when you do use library boot and you ask for some confidence intervals based on the results there, then it's going to automatically calculate your bias corrected and accelerated interval. And this is kind of just the recommended confidence interval to use, just out of the box if you're not going to do any deep thinking about your results. The software will handle it for it, and it's typically recommended as your default confidence interval in most scenarios. Okay. All right. So let me give you your second view quiz answer, which is the letter C. C as in cat. C as in cat is your second view quiz answer. And so here we'll just do a couple more examples of Bootstrap using library boot. Here I want to do a bootstrap of the median. Okay, so let's say we want a confidence interval for the median of a numeric variable. There isn't a nice straightforward value we use for the sampling distribution for the median. It's actually kind of tougher. We think when you learn about values of center, mean and median are often presented together. Mean is very simple, you add them up, divide by how many you have. the median is just the center value, but it's actually a lot more involved as far as calculating it. Because you can imagine, like, let's say you have streaming data coming in, right? Like a new data value shows up every second. Okay, if you wanted to just update your mean, it's very easy. You just you have like a running sum on the top and a running count of how many observations you have. So the new observation comes in, you add it to the numerator, add 1 to the denominator, you recalculate your mean that way. Okay, what about the median? What do you have to do there? Okay, every new value that comes in, you have to basically, you insert it into your thing, and you have to like resort your values so you can find the middle value. Okay, and then I mean, there's ways you can kind of optimize this, and you say, okay, I have a count of what's above and what's below the median and things like that. But then if you need to, like, if you say, okay, I do need to shift my median, then you have to find the next value, which requires you, again, you to sort all of your values. And so if you have a million observations already and a new observation comes in, you've got to resort all million. So it's just a lot more computationally expensive. But anyway, and we don't, have a nice little, as far as I know, is there a theoretic distribution that we would use for the sampling distribution of the median? I don't know. People who just took 100B, is there anything for that? So anyway, bootstrap. This is, to wiggle our way out of these tough analytic situations. We just say, let's bootstrap it, okay? And so, for our data, we'll use this built-in air quality data set. It's got a bunch of different kind of things, but we'll look at the ozone levels, okay? And here's just kind of the different values that we have in air quality $ozone. The minimum value is 1, okay, but the largest value is 168, indicating, there's going to be some skew. My median is 31.5. First quartile is 18, but my third quartile is 63.2. So we got some skew here. The median probably makes sense, right? The mean is much greater than the median, also indicating skew. So anyway, I'm going to just load in my data. I'm going to throw out missing values, okay? And then I need to have a function that is going to calculate the statistic of interest. And in our case, our statistic of interest is just the median of my data, okay? However, this function that I use has to be adapted to take in the data and the indices, all right? So my data is just going to be this vector of ozone values, okay? But the index, this is going to be resampled. This will be provided by the boot function, but I need to subset my data using the index. So I'm going to have this just one line here that says take the data and subset using the indexes. Okay, so I've got data, square bracket, indices. That's going to be my resampled data. I say give me the median of that and return that. That's going to be the entirety of the function. Okay, this is going to calculate the median of my resampled values. That's it, okay? So don't be intimidated by the fact that you have to write your own statistics function. It's just subset your data according to the indices. In this case, data is a vector, so I'm going to just do data, square bracket, indices. That's going to be D, and then we're going to calculate the median on D. All right, then I run the bootstrap. So I do boot. My data is the vector, air quality $ozone. The statistic I'm going to calculate is going to be median underscore function, which is the function that I just wrote here. And then I'm going to say I want 2,000 replicates. And then the results, the original median is 31. It's apparently biased. There's a standard error. I can say, all right, give me the confidence intervals. So here I say boot.ci, and I want the basic, percentile, and BCA intervals. The text got misaligned here, but my basic interval goes from 23 to 39. My percentile interval goes from 23 to 39. And my BCA interval goes from 23 to 37, okay? So that's that. That's the bootstrap confidence interval there. So yeah, that's what we have. Okay, here's just another example where I'm going to bootstrap the correlation, okay? So here we want to create an estimate of the correlation between two variables. We'll make a confidence interval We're not going to assume normal distribution. Here we're going to look at the data set MT cars, another built-in data set, and we're going to look at the relationship between engine size, displacement, and gas mileage, MPG. And so the MT cars is like an old data set looking at like cars from like the 1970s where they have like these big engines and terrible gas mileage. Like cars have come a long way since then, in the 50 years. You know, we still use a combustion engine. I mean, we have electric vehicles now also, but even the combustion engine is like much more efficient than before, okay? And we can generate a lot more power with less engine size, higher gas mileage. Things are much more improved. But anyway, we expect to see a negative correlation. Bigger engines will have more displacement, but lower gas mileage. Smaller engines will have less displacement, but better gas mileage, okay? So anyway, again, I need to write a function that is going to calculate the statistic of interest. I want to just calculate the correlation between MPG and displacement. The function has to take in our data and subset it according to our indices. And here, data is a data frame. So to subset according to the indices, I'm going to do data square bracket indices comma, and that's going to subset the rows, okay? And again, Bootstrap is expecting our data to be in tidy form where each row is an observation. So I subset my data according to the indices that gets passed to it. That's going to be D. Then I just want to calculate the correlation between the MPG column and the displacement column. So I do $d sign MPG, $d sign displacement, correlation between that, that's going to be the value I return. So that's going to be my correlation function. And then to run Bootstrap, I say the data is going to be MT cars. The statistic I want to calculate is going to be found using the correlation function. Give me 2,000 replicates. Okay, so here's my boot correlation. The original correlation I get in the original data was negative 0.847, and these are the resulting confidence intervals. I can say give me Bootstrap confidence intervals on the correlation results, Bootstrap results here, and I get my basic interval, my percentile interval, my bias and corrected interval, okay? Bias corrected and accelerated interval, I guess. So my basic interval goes from negative 0.2987 to negative 0.7839. My percentile interval is negative 0.9112 and negative 0.7664. And my BCA is negative 0.9028 to negative 0.7445. Again, if you're not sure, kind of the recommended one is the BCA interval. All of these things, remember, correlation goes from -1 to +1. And the correlation of our original data is at negative 0.847. So there's kind of a hard cap, lower bound of -1, and we see, you know, our different intervals are kind of, you know, negative 0.847 is already kind of close to -1. So the lower bound of our interval, you know, is just not going to touch -1, and each of these things kind of have their own kind of, you know, correction factor to avoid getting too close to -1. So, you know, my bias corrected one is negative 0.9028 to negative 0.7445. That's probably going to be our recommended interval here. Okay, and that's what we have. And yeah, these are going to be different from, you know, if you assumed a normal distribution on the data, which probably for this data set, yeah, we probably don't want to assume normality there. Okay, that is it. Let me give you your third and final view quiz answer, which is the letter B. B as in bear is our last view quiz answer. And then we will go ahead and end lecture here. Have a great rest of your day. Have a great weekend, and we'll see you next week, week 10.